Swayam Prabha. Digital India. Educated India.
Hello folks, welcome to yet another session of our NPTEL on Nonlinear and Adaptive Control. I am Shrikant Sukumar from Systems and Control, IIT Bombay. We are as usual in front of this very nice motivating background image of this rover on Mars, and we expect that we are moving forward towards learning how to analyze and design algorithms that are going to drive autonomous systems such as these. So without any further delay, I'm going to sort of try to recap what we have done until last time. So at the end of the last week's lectures, we started looking at stability in the sense of Lyapunov, right? And in the beginning of it, we sort of tried to look at what is the notion of existence of unique solutions, which is sort of a critical ingredient for us to be even able to talk about existence of stability and so on and so forth, and other properties of any differential equation for that matter. All right. Once we understood that we require these Lipschitz notions in order to talk about stability and talk about existence and uniqueness, we went on to define the notion of an equilibrium and especially the notion of an isolated equilibrium. We try to understand why this isolated equilibrium is such a key concept in studying stability, and the fact that non-isolated equilibrium doesn't even allow us to talk about convergence and comparison with one specific equilibrium point, because there are so many of them arbitrarily close to each other. All right. Now, so this is what, or this is why, this was such an important notion. Okay. Once we had under our belt the notion of an isolated equilibrium, we were ready to talk about the first definition, which was stability in the sense of Lyapunov. And this is in the format of very, very standard format of an epsilon delta definition. All right. So this is the standard format for any stability definition that we will be seeing now or in the future. Okay. So what is it? It sort of comes as a challenge question. That is, given every epsilon positive or even any epsilon positive, I should be able to generate a delta which depends on possibly the initial time and the epsilon, and this is also a positive number, such that if my initial conditions start within a delta ball of the equilibrium, then my state remains within the delta ball of the equilibrium, or remains within the epsilon ball of the equilibrium for all time. All right, and we do this very nice illustrative picture in order to understand this notion. We also understood that delta has to be less than or equal to epsilon for things to make sense. Okay, so once we had the notion of Lyapunov stability, right, understood, right, we want to look at the notion of uniform stability. So what is it? So this is where we begin today. So what do we have in uniform stability? The only difference between Lyapunov stability and uniform stability, or uniform stability in the sense of Lyapunov versus stability, is the word uniform, of course, right? So we added a new word, a new qualifier, if you may. So that's of course one new thing. And what does it entail, this uniformity? This uniformity is with respect to the initial time, right? So if you look at the deltas that you get in each of these definitions, there is a difference that the delta in the case of uniform stability is independent of the initial time. Okay, and so this is what is the difference. Everything else is exactly the same. Given an epsilon, there has to exist a delta which now depends only on epsilon, not on T naught, such that if my initial conditions are within the delta ball, my solutions remain within the epsilon ball of the equilibrium for all time. So this statement and this statement are absolutely the same. If you notice, there is no difference between the two. The only difference lies in the delta, right? Wherein here it was dependent on T naught and here it was independent of T naught. Okay, and we will of course see when such a situation arises. We will look at examples subsequently of when we have one property and not the other. Okay, now one of the important things to remember is that we say that the equilibrium is unstable, okay, if it's neither stable nor uniformly stable. If the equilibrium XE does not have either of these two properties, right, then we say that our equilibrium is unstable. Okay, then we say that our equilibrium is unstable. Okay, so in order to sort of illustrate these properties, let us look at an example, a very, very standard textbook example from the book by Vidyasagar. Right? This is from Vidyasagar's book. Yeah, you can find it in this book of nonlinear systems. By Vidyasagar. All right, this is in the chapter where, you know, where stability and other notions are in fact being defined. Okay, a very, very, very standard example in that sense. So what is it? It's a very simple scalar system, right? You're given x as a scalar quantity. So I will sort of explain. I'll sort of explain. X is in our real numbers. Okay, and you have some initial condition, of course. X t0 is just your initial condition. I'm not denoting, it's not denoted here as anything else but x t0. All right, so its x dot is 6t sine t minus twice t times x. Okay, so and of course, like I said, it's a real number with some initial condition at initial time. Now if I once I've chosen an initial time and this initial state, of course I can integrate this, right? This is very easy to integrate because this is simply dx over x and this is 6t sine t minus twice t dt, right? And I can of course integrate both sides. Yeah, so from x t0 to xt on the left and t0 to t on the right. So this is not very difficult to do. I can actually carry out this integration, and in fact the outcome of this integration is this expression. Okay, so the outcome of this integration is exactly this expression. You see, okay, let's not be very worried. So the left hand side actually gave me log x, right? So basically from this guy I got log x, yeah, log x divided by x t0. Okay, therefore I got an exponential here, right? Because I had log x divided by x t0, and therefore I got an exponential here when I took it to the other side. And the integral of this was simply 6 sine t minus 6t cosine t minus t squared, and this is corresponding to the initial time, right? This is corresponding to the upper limit t, and this is corresponding to the lower bound t naught. Okay, very standard in a definite integral. Okay, so now it's a rather long expression but not too complicated. You can actually take a derivative with respect to time of this guy and you can see that it satisfies your differential equation. Okay, it's not difficult to see that it does satisfy your differential equation. Okay, excellent. Right. So I would advise you to do that diligently. Take a derivative here and verify that it satisfies the differential equation. One thing is obvious: if I plug in t0 instead of t here, the exponential term is in fact 0. Therefore x of 0 is 1, and so xt0 is xt0. That is, it's verifying that initial condition, and after taking a derivative I can also verify that it satisfies the differential equation. Therefore this is indeed the correct solution, right? The unique solution. Alright, this is important to us, that this is a unique solution. Okay, so what is the equilibrium in this case? What is the equilibrium? We didn't discuss that. Let's see, let me try to get rid of this. Yeah, so what is the equilibrium? X sub b is zero. Okay, so 0 is the equilibrium, because you can see the right hand side is 0 exactly at x equal to 0 for all time. Okay, so 0 is the equilibrium. Great. So I can succinctly write this quantity, right, as this. Okay, now what have I done here? What I have done here is I have defined a quantity gamma as x of minus 6 sine t0 plus 6 t0 cosine t0 plus t0 squared. Okay, so notice, so this is what I have done. I have defined a new quantity gamma, okay, which is just taking the initial time component of the exponential, pulling it out. Okay, and notice that this is a constant whenever t0 is fixed. Once I fix the initial time, gamma is a constant, so therefore I have written it as such. Okay, so I have xt0 multiplying gamma, and now only a exponential containing only a function of the time t. Okay, so again let's go back to our, remember we talked about this abuse of notation, right? You see that the solution does depend on initial time and also on t and also on initial state. Okay, however, when we sort of write the left hand side, we just say that it's a function of time t. Okay, so this is an abuse of notation, but we've already understood what this is, and therefore we are okay with it. But we do remember in our minds that the right hand side does depend on the initial time as well as the initial state. Okay, all right, excellent. So once I have this sort of assignment, this definition, and I have this relatively succinct expression for x of t, the solution, I want to remind myself that there exists some finite time capital T beyond which this is negative, right? Why is this? Because t squared dominates 6t cosine t and 6 sine t. Yeah, so this is just a property of the functions involved. If you look at this minus t squared, this is a quadratic term in t, so it's going to grow really fast, whereas this one is a linear term in t with a cosine which is of course going to fluctuate only between plus minus 1. So it's just a linear increase in time, and this is just a sinusoid term which is going to stay between plus minus 6, and this is of course going to stay between plus minus 6t. But this term is going to rapidly increase as t squared. Okay, so beyond a certain time you can be sure that this function is going to become negative because there is a minus sign attached to the t squared. Okay, So therefore there exists some capital T such that beyond that time this quantity is negative. Okay, so this is a rather critical thing for us. Okay, so what do? We take this time and we find the supremum of this function. Okay, what is it? So we say that m equal to 0 and we denote m as, so this is actually a definition, we denote m as the supremum from initial time to cap t of this quantity, 6 sine t minus 60 cosine t minus t squared. Now why do I find the supremum only over this time? Because I know that this quantity is possibly positive only in this window. Only in this window is this quantity possibly positive. Beyond it, it is definitely negative. Okay, so if I try to plot this function, just to make things more clear, if I try to plot this function, I can expect it to look like so. This is the time cap t. Okay, so this is this function right here on the y-axis. Okay, it should be evident that at t equal to 0 what happens? Let's see. In fact, let me actually be careful. I should not have done that. Okay, so let's say that this is t equal to t0. At t equal to t0, say it's some positive quantity. I don't know what it is. Yeah, so this is, as you can understand, this term is exactly going to be 6 sine t0 minus 6 t0 cosine t0 minus t0 squared. That's what is this guy. Alright, and then beyond that, say it's positive for some more time. Okay, and then I have this peak. This peak is what is m, then it drops, and I know for sure that beyond this time cap t, it is definitely becoming negative. Therefore, I need to consider the supremum of this function only in this window. Okay, if I want to find the supremum or maximum value of this function for all time, okay, if I want to find the maximum value of this function for all time, I need only to look at this window t0 to capital T. Right? And that's what I do. I look at only this window t0 to capital T. Okay, great. So I know that this function is definitely below m. Now what I claim is that if I choose if I'm given an epsilon positive, I claim that a valid delta is this guy. I claim this is a valid delta. Okay, I claim this is a valid delta. Why? Why is that? This is true because if you assume that your initial condition is delta away from the origin, okay, what does that mean? That means that my absolute value of x0 is less than delta, which is equal to epsilon over gamma e to the power m. Okay, then what can I say about the solutions? Let's look at the solutions right here. I'm going to write right here. Okay. So absolute value of xt, I'm taking absolute values on both sides and I'm going to freely use the triangle inequality. So this is going to be equal to gamma x t0 exp of this whole thing right? So absolute value of this whole quantity, right? But I know for sure that this is less than or equal to absolute value of gamma absolute value of x t0 times the absolute value of this whole guy. By my usual triangle inequality. Now I know for sure that this guy is upper bounded by m, because of what I just, how m is defined. This guy is upper bounded exactly by m. Okay, so what do I know? I know that this is less than equal to, also notice that gamma is basically, gamma is basically an exponential of some quantity, right? So gamma is basically exponential of some quantity, so therefore it is always positive. So I can get rid of this. Then I have absolute value of x t naught, and this is capital M. Okay, this is capital M. Now once I have this, you see, so there is, I have not been, this is not very carefully done here. This is actually, this should be xt0, because that is what we are using. Okay, this is what xt0. This is what we have been using. All right, so once I reach this point, that x of t is less than gamma m xt0, that is here. Okay, I can substitute for absolute value of xt0, which is chosen to be less than delta, right? This guy. So once I substitute this here, what do I get? The gamma em cancels out, and I get that xt is less than epsilon. Exactly as we required. Exactly as we required. Okay, so great. So we have been able to show that given an epsilon, I can find a delta such that if my initial conditions start within the delta ball, my solution remains within the epsilon ball. Okay, the important thing to remember is that the delta and hence gamma depends on T0. Yeah, so in the definition of delta, I have a gamma, and if you notice, the gamma was defined as such, and this is dependent on T0, and therefore delta is also dependent on T0. Okay, so what have we shown until now? We have shown that until this point, if I see, let me be careful here, until this point we have shown stability of 0 in the sense of Lyapunov. Okay, in the sense of Lyapunov. Now what I want you to notice now, okay, so we have already shown stability. So the next question, of course, is it uniformly stable? Yeah, because those are the only two definitions we've done. So those are the only two things we can in fact test. Okay, so the next question is it uniformly stable? Right. So what I would like you to notice is that the only dependence of delta to T0 comes from gamma. Okay, that's the only way. So we look at gamma itself. So we know that gamma is this expression, right? Now what can I say about gamma as T0 goes to infinity? As T0 becomes really large, you can see that gamma also goes to infinity. As T0 goes to infinity, gamma goes to infinity. This was sort of obvious and expected because the sign of T square is opposite in these two terms. This is very standard when you do a definite integral, right? So what happens is T0 squared, again the quadratic term, dominates every other term. So if I push my initial time larger and larger, then my T0 squared dominates everything else, and the exponential also goes to infinity. In fact, very fast. Yeah. So if T0 goes to infinity, gamma T0 also goes to infinity. So this is something you should remember. Now what we are claiming is that we cannot choose a uniform delta independent of T0. Alright. So and why we say that? We say that because as T0 becomes large, gamma goes to infinity. Okay. So let's see why this is. Let's try to understand just by some crude example. Okay, why this is. Okay. What am I saying? I'm saying that the delta we chose was epsilon over gamma e to the power m. Let's see. I'm sorry. I think there was a slight error here. This is not gamma m. Okay. I'm sorry. Here it should not have been gamma m, but this should have been gamma e to the power m. Okay, because the exponential was there, right? So yeah, so there was an error there. That's okay. All right. Now the delta we chose was epsilon over gamma e to the power m. Okay. Now what are we saying? That we cannot choose a uniform delta for all initial time. Okay. So why are we saying this? We know one thing for sure, that as beyond a certain time, beyond say t0 greater than equal to some cap t, gamma of t0 increasing function. Okay, gamma of t0 is an increasing function. This is not difficult to again claim, right? Why? Because if you see, the t0 square is dominating, so beyond a certain time, this entire quantity, right, this entire gamma quantity, this entire quantity in the exponent of gamma, okay, is going to become positive and remain positive, and it will continue to increase. Okay, so it's going to be an increasing function. Okay, another way of looking at it would be to sort of try to take a derivative of this exponent and confirm it. Alright, which is also not a difficult thing to do. So if I take the derivative, also I can confirm, right? So what is the derivative here? Very quickly, this will be of this exponent. So I'm trying to take a derivative of this guy. D dt is 6 cos t0 minus 6 cos t0 plus 6 cos t0, okay, minus 6 t0 sin t0 plus twice t0. Okay, so here these two will cancel out and I'm left with just this much. Okay, twice t0 minus 6 t0 sin t0. Alright, so let's try to see what happens here. Is this going to be always increasing? Let me be careful here before I claim this. This is going to be t0, so this is going to be t0 times 2 minus 6 sine t0. I see. So this is not evidently increasing, is it? Let's see if I have missed something here. 6 cos t0 plus 6 cosine t0 minus 6 t0 sine t0. Yeah, that seems about right. Plus twice t0. Okay, and this is going to sort of be subtracted by this quantity Okay, no, this is not evidently increasing unless I'm missing something. All right, okay, so this is something I need to verify. So in any case, we are sort of almost at the end of the time for this lecture. So what we will do is we will sort of continue our discussion on whether this is uniformly stable or not in the next lecture. All right, so anyway, what have we seen today? So what we have seen today is the definition of uniform stability, which is slightly different from stability in the sense that it is uniform with respect to the initial time. The delta doesn't depend on initial time. And we started to look at an example, a very nice example where we could actually solve the differential equation and verify stability at this point. We are now trying to check whether the system is uniformly stable or not, and this we will complete next time. So that is it, folks, for this time. We will meet again soon. Thank you.